Hey there, and welcome to The Explainer. So, have you ever wondered how data scientists actually predict the future? Like, how do they take a massive, chaotic spreadsheet of real world numbers and turn it into a reliable forecast? Well, today, we're going to demystify some of the most complex statistical concepts out there. And to make it easy, we're going to treat data science just like building a mathematical house. We'll start by pouring a solid foundation, then we'll learn how to spot structural cracks, and finally, we'll bring in the inspectors to make our repairs. Let's get into it. So here is our roadmap for the build. First, we're going to predict with ordinary least squares and prove it's the gold standard using the Gauss-Markov theorem. Then we'll hunt for two major structural hazards. They have completely intimidating names: tangled multicollinearity and wobbly heteroscedasticity. But honestly, don't worry, we're going to break them down super simply. And we'll wrap up by untangling things with VIF and run in the Bruch-Pagan test to fix our model. All right, part one, predicting with ordinary least squares. Because before we can build walls or a roof, we absolutely need a fundamental tool to make sense of messy data. So how do we mathematically predict the future? Well, to answer that, we need a way to take scattered data points and find the most logical path right through them. Picture trying to predict the price of a house based strictly on its square footage. If you plot 50 houses on a graph, those dots are going to be scattered everywhere, right? So how do we draw a single, reliable line through that messy cloud of dots to predict the price of the 51st house? That brings us to our foundation, ordinary least squares, or OLS. Now, OLS is just a fancy way of saying drawing the best fitting line. When we draw a line through our data, our prediction is never going to perfectly hit every single dot. The distance between our line and the actual dot is our mistake, or what statisticians call a residual. OLS does something very clever here. It literally squares all those mistakes. We do this so any negative numbers turn into positive ones. That way, they don't just cancel each other out. Then, it mathematically finds the specific line that makes the total sum of those squared mistakes as absolutely small as possible. It is the concrete foundation of our mathematical house. But listen, to build a house that doesn't collapse, our OLS foundation has to follow a very strict building code. Our sources highlight four primary assumptions, which you can remember with the acronym LINE. L-I-N-E. First, linear. The relationship between our variables actually has to be a straight line. Second, independent. One prediction mistake shouldn't influence the next one. Third, normally distributed. Our mistakes should roughly follow a bell curve, meaning most mistakes are pretty small. And fourth, equal variances. The spread of our mistakes should stay consistent across all our predictions. Follow this code and your foundation is rock solid. Okay, moving to part two. With the foundation poured and our building code followed, we need to prove to the city planners that our blueprint is the best one available. Enter the Gauss-Markov gold standard. This introduces us to an incredibly important concept called BLU, which stands for Best Linear Unbiased Estimator. In statistics, an estimator is basically just our mathematical formula for guessing the truth. What the Gauss-Markov theorem mathematically proves is that if you follow those line building codes we just talked about, your OLS model isn't just decent, it is mathematically the most accurate and fair linear model possible. It's the gold standard. And this comparison brilliantly illustrates what blue actually means in the real world. Think of predicting data like throwing darts at a dartboard. An unbiased model means that, on average, your darts are centered around the bullseye. You're not systematically pulling your throws way off to the left or right. A minimum variance model means your darts are clustered really tightly together rather than scattered wildly all over the board. The Gauss-Markov theorem proves our OLS foundation is the best because it gives us the tightest possible cluster of darts right over that bullseye. It's fair and it's consistently precise. Now for part three. Because even the best blueprints can suffer from overlapping support beams, which brings us to the first major structural crack in our model: tangled multicollinearity. Multicollinearity happens when two or more of the variables you're using to make your prediction are highly correlated with each other. It's kind of like having two employees doing the exact same job on a factory assembly line. The factory still produces widgets, so the overall prediction technically works. But when it comes time for performance reviews, you have absolutely no idea who to credit for the work. Because they move together, the math gets totally confused, making your model unstable and the estimated impact of each variable highly unreliable. And the crucial point here is that this overlap doesn't just come from one place. As our sources explain, it can happen organically through data-based multicollinearity. This is like having flawed raw materials. It happens in observational studies where things naturally just move together in the real world, like a person's income and their years of education. Or it can be structural, which is honestly just a mathematical artifact we accidentally create ourselves. Like if we use age as one predictor and then we square that number to create a second predictor called age squared, well, we've just built two overlapping support beams. So for part 4, we need to untangle these variables with VIF. Basically, to find these overlapping support beams, before they compromise our build, we gotta call in the building inspector. Our primary inspection tool is called the variance inflation factor, or VIF. It essentially measures how much the variance, or the uncertainty, of our estimates is blowing up like a balloon because of these overlapping variables. The rules of thumb here are super clear. A VIF score of exactly 1 means perfect independence. The employee is doing their own unique job. Anything over 4 means, hey, you should probably investigate this. And a VIF over 10? That means we have a serious structural hazard requiring immediate correction because our variables are way too tangled. Let's look at a really concrete example from our source material, using a health data set. Let's say we are trying to predict something using height, weight, and body mass index, or BMI. For height, the VIF is 5.33. Weight is 8.42. But BMI is blasting past 10. Why? Well, because BMI is literally mathematically calculated using height and weight. Our weight and BMI employees are doing the exact same job. To fix this, the best remedy is usually just to fire one of the overlapping workers, which just means we remove one of the offending variables from our model entirely. All right, part 5. We've sorted the overlapping beams, but now we're walking through the house and noticing wobbly, uneven floors. This brings us to pitfall 2, wobbly heteroscedasticity. Heteroscedasticity is a massive word, I know, but it really just means unequal scatter. Remember our building code that said our prediction mistakes must have equal variance? Well, this violates that. Imagine predicting a broke college student's food budget versus a billionaire's food budget. The college student's budget is super constrained, so our prediction mistakes are going to be tiny. But a billionaire? They could spend $10 on a burger or $10,000 on caviar. As income rises, our prediction mistakes fan out wildly, taking on the shape of a megaphone. When this happens, our standard errors become totally unreliable. And that means we can't trust our confidence intervals, which are the safety margins we build around our predictions. Finally, part 6, we need to fix those wobbly floors once and for all. Let's bring in our final inspection protocol, the Bruch-Pagan test. To officially diagnose this megaphone problem, we run the Bruch-Pagan test, which is an ingenious 4-step process. First, we build our standard model and calculate all our prediction mistakes, or residuals. Second, we square those mistakes to make them all positive, so we're only looking at the sheer size of the error. Third, we run a brand new secondary test called an auxiliary regression. But this time, we try to predict the size of the mistakes using our original variables. Finally, we check our p-value, which is essentially a statistical probability score. If that score is significant, it means the mistakes are growing in a predictable pattern, like a megaphone. If so, we've definitely got heteroscedasticity. So does a failed Bruch-Pagan test mean our mathematical house is pure garbage and needs to be torn down? No way. As our sources point out, heteroscedasticity doesn't bias our actual predictions. It just messes up our confidence intervals. We can easily repair our wobbly floors using some robust mathematical fixes. The most common fix is applying heteroscedasticity consistent, or white standard errors, which basically corrects the math behind the scenes. We could also use weighted least squares, giving less weight to the highly variable data points. Or we can just mathematically transform our data, like using a log transformation to beautifully squash that megaphone shape right back down to a straight, even tube. And there you have it. You now understand how to lay a mathematically perfect OLS foundation. You know how Gauss-Markov proves it's the gold standard. You know exactly how to spot overlapping beams using VIF, and how to repair wobbly megaphone floors with a Bruch-Pagan test. You are leaving this explainer equipped with the ultimate analytical toolkit. So the only question left is, now that you have the blueprint to build a perfect prediction model, what invisible forces in the real world will you predict next? Thanks so much for joining me on this explainer, and I will catch you next time.